G'day all. I'm going to give you a little tour of what I've done for week 9. So this wrapped up we had a little break from publishing submissions while you did your assignment. And so we're catching up a little bit on a number of things. A fair chunk of things going on in here. I wanted to show you my approach as well as my solution. Okay, so first of all, I started with the language that I wanted. At this point, we are looking at putting variables into the language, which we've all been hanging out for, because our code was very difficult to understand. So if I look at last time I left my code, Devlin's Creek expression looked like this, which was not fun to play with. But by switching over to variables, this is what I would like my Devlin's Creek to look like. If you have a look at your copy of the Devlin's Creek map, this will make a bit more sense. But the idea is that each part of the creek gets its own. I name each literal. I don't just have them floating around. Variables are helping me. All they're doing is naming each literal. I'm never changing a variable. So they're not really varying, but maybe they're constants, but we're doing them as variables. And I've got my plus and my arrow and my more complicated literal in this example. That's the one I decided to go on with, partly because most people who submitted their assignments had done the plus and the arrow as well, the confluence of rivers and the combination of rivers separately. So I felt confident being able to show you this one. Plus there's a lot of fun things to think about in this version of the literal once we get to evaluation, which we are touching upon this week. So I rewrote each of my examples to be in the form I wanted before I did anything else. I chose to use an equals for assignment and a semicolon and a var, just all the same things from LOX, which seems sensible enough. I did support a statement expression where there's just a statement in there, which LOX has partly for the interpreter, the REPL. And so I ended up with these three ones. An expression only, putting that expression into a variable, a little creek system that's got a plus, and a full example of the Devlin's Creek example, which has pluses and arrows. I don't have an output variable. You'll see why later on. I noticed in the assignment a few people did that. So once I've got that, I go write the parser, the grammar that's going to support that. So I jumped over to my parser file where I had a grammar at the top. And I expanded out my grammar. So the grammar I had before this was actually just that part, not very much at all. And all I did was copy exactly what the book did for adding variables, and I left out all the other different types of statements that it thought about. So a program's a series of declarations. A declaration's a variable declaration or just any other statement. A statement, I've only got one kind, it's an expression statement, because I haven't got loops or ifs or anything like that yet. Okay, expressions could be assignments. This one is an unnecessary grammar because all it does is just say an expression is an assignment and an assignment is a this, but that's because I copied it over from the LOX one where an expression could be assignment or other things. But I've simplified it and just ended up with this one. And then assignment's either an actual assignment or it's one of the other expressions. And I've had to also add, and I've got to remember all the way down the bottom, because I forgot this at first, that once you've got variables, you have to allow a new type of literal, it's not really a literal, a new type of value, which is just an identifier by itself, so I added that. And there was a process of just adding all of these in according to the parsing. And again, I copied most of these over from the, I copied by typing them out, but I copied most of these over from the LOX version, and they all just came across normally. But as I started to fill it in, I realized what types of new AST nodes I needed. So you'll see here that as I'm going down, I'm realizing, look, I need a statement. I don't have statements yet. In fact, the first thing I realized once I was looking through the book was that this parser isn't a parser for expressions anymore. It's a parser for a list of statements now. The final thing is a list of statements. So I didn't even have statements at all. So I jumped over to my generator code, and the generator code had most of these already, but I had to add in statements. And so there were two types of statements. There was just the expression statement, And then there was the variable declaration statement. Again, there's nothing here that's not in the locks example. It's just less than the locks example. And then I had to add in an assignment expression and a variable expression as well. Keep in mind that this flow expression was the one I worked on last time, which is my new literal for river flows. Then I had to rerun this. Take a look at some interesting stuff here though. Where's the interesting stuff? Oh yeah, on my flow, I switched these from object to double because once I got to evaluating, I had to start doing that. We'll talk about that more when we evaluate. So with those AST nodes in, my parser can do its job. And I go back to the parser to see what decisions I made. So when I parsed a statement, well, the only thing it can parse as is an expression statement. An expression statement is an expression, then a semicolon. A declaration can parse either as a variable declaration. If that fails, it just does another statement. A variable declaration consumes an identifier and then optionally has an expression afterwards. All this is the same as locks, right? So I've followed locks stuff over. It's been really easy in this case because everything from locks worked really well here in statements. Once I'd done all that though, my AST printer went chunky because it's it implements an expression visitor. When we left it, it was implementing an expression visitor. And I just added two new types of expressions, right? I added the assign expression and the variable expression. So it didn't have visitors for those, so I had to add them. And I added those here. And so I just came up with some sensible thing for my AST printer to do. Also, those are statements. I just added some sensible things for the AST printer to do when it sees an assignment. But I decided as well, I'm going to expand upon it and make it a visitor for statement lists as well. Sorry, for statements as well. So I made it a statement visitor as well, but that meant I had to put in the two statement types, which I did. Now in the textbook, they stopped extending the AST visitor, but I wanted to keep it for reasons you can see down below in my console. Because my version of locks and every time I run it, it spits out all the intermediate information for me to help me. It's continuing to spit out my entire list of tokens, and it's continuing to spit out the abstract syntax tree that was parsed. So I wanted my abstract syntax tree printer to stay current and work. And so I chose to make it a statement visitor as well as an expression visitor, and now it can do everything that the parser can spit back. So with that done, I was able just to try my parser. I did have to make a few changes over in locks to make that work. Ignore the commented out bit because that's coming for the evaluation. But you can see that the parser parses a list of statements now instead of an expression. And but the AST printer knows how to print that program. Cool. So with that done, I was able to recompile the program and then just run it on my examples. So this is my way of testing if it's working. So I would run it first on the expression only one, my smallest one. And I got the tokens out and I checked that those were what I expected. I got the AST out and I checked that that was what I expected. So this is just a expression statement being parsed, and result is not being printed yet. So I better recompile that. Yeah, we want the version that doesn't have results. Okay, so then I run it again for my slightly more complex one, which is Tiny. Tiny, if you recall, I've got to split this. Okay, Tiny, if you recall, looks like this on the right. So it's got a single variable only. It's got that logical expression, and I look down in my code, and that's what it's doing. It's the tokens are coming out correctly, the AST is coming out correctly, and there's a single statement in here, so there's a single statement being printed in the AST. My next example was small, and so that had three different variables, two that were literals and one that was a plus, so I run that. Now, when I was doing this myself, I didn't just put it in and it worked. There were bugs and all kinds of things that I went around. But what I'm trying to show you here is the structure, because in 99% of this part, it's just come straight from the text. So it was really the way I went about incorporating that from the text that was important. And the addition to the AST. So I'll show you a little bit more about the AST because there was a little bit more of interest happening over there. So you can see that the main print statement here takes a list of programs and then it loops over that list of programs. It's got an empty string to start with. It loops over that list of programs and just gets the string from each statement and jams it on. String from each statement, jams it on. String from each statement, jams it on. And that's why I'm getting the 3 statements appearing on my console above each other, because there are 3 statements in this AST. And each statement is got an expression inside it, and that's what we see. A thing to keep in mind at this point, once we hit statements, we've been thinking of ASTs as trees, and they are, I mean, abstract syntax trees. But once we add statements, at the top level, it's a big list of trees. You can still think of that as one tree with many children, but I prefer to think of it as a list of trees, one for each of the statements in the program, and we process them top to bottom. All right, and then finally, my larger example, and it really gets going there. Now we can really see the benefit of having the language support. There's a lot going on in here that the code is doing for me. The token list is long, but I can still check my parsed output, my AST, and agree that it's right. And this is why I always build up from the smaller examples to the more complex ones, because there's a lot going on and I've got to warm myself up to understand the output. Okay, so my language is now supporting variables up to the parse phase, but we also want at this point to start doing an evaluator or an interpreter. I'm going to mix those 2 words up, evaluator, interpreter, they're the same thing in this context, that turns the abstract syntax tree into a result. And here's the number 1 key decision I made in mine that you might not have made in yours, but I think it's super valuable. It worked out well for me, so I'm going to encourage you to do it. In the textbook, the final result of a LOX program is an object. So the evaluator turns AST nodes into capital O objects. But in my language, there's really only one type of value. It's one of these river flows. Everything's a river flow. I don't have the difference between booleans versus numbers. I might add that later, but for now I don't. Everything's a river flow. So I decided that my evaluator was going to take AST nodes and turn them into river flows. And so the first thing I did was make myself a river flow object. And that turned out to be really useful. Okay, so my river flow object is just represents those 10 numbers that are the predicted future flows if a millimeter of rain falls on this particular area. So I made it myself. 10 doubles, and I made a constructor for it. And this constructor is doing the hard work of converting this notation into 10 numbers. I've gone with a broken one that ignores the variance for now. It uses the middle position and just puts all of the flow on the middle position. But when you construct a flow with those 3 numbers, it makes a 10-element array with the numbers representing the way you've described it. And that's all a flow is, but that's the only value that's being passed around inside my language, so I decided to go with it. There's a bit more down here that's needed for later, but that's all that matters right now. So now my interpreter is an expression visitor and a statement visitor, just like the one from the text was, but it's an expression and statement visitor that not one that generates capital O objects, one that generates capital F flows. And that meant I had more changes to make from the book, but they are really useful changes because they forced me to think the type system started giving me all the errors, and I could follow through those errors and make decisions about what I wanted to do, and it really clarified my mind about what this flow is and the way a language that executes it would operate. I jumped straight to having environments because I got the variables and I want to run an evaluator. So that was like the end of chapter 9, I think it is in the book. So I brought all that over. The environment came over almost the same. The only thing needed for the environment was that it's not a hash map of string to object. It's a hash map of string to flow, because I went all in on flows. And so flow went there and flow went there. But otherwise the code is identical. And the interpreter has to know how to visit both expressions and statements. And ultimately, we need a top-level thing that can take in a list of statements, because that's what a program is, and then visit each one at a time. So that's precisely what this program does. It visits each one at a time. And now here's the next big decision I made. I said, what's the result of this program? In locks, there is no result. Like, the interpreter, when it needs to evaluate an expression, it gets back a capital O object. But for statements, there's no output. It's a void, right? I decided that yes, the result of a statement is still void. The result of a statement doesn't make sense because statements just update the environment. But once the program is finished running all the way to the bottom, the final output is going to be every variable I found and the final value of that variable. It's almost like a little debugger. It's just showing me the final state of the program. And so I said, after you've looped over all the statements, just return the environment values. Even if there's an error, please return the environment values. And I said that the output from the interpreter is not a void. It's the whole environment, like the inside of the environment, the map string to flow. That was another big decision that really helped in my program. So I copied over, again, typing them out again, but copied over lots of bits and pieces, and most of them came over exactly as you would expect. I don't need the is truthy, that's why it's underlined, because I don't have booleans at this point, and is equal, so there's a ton of things I'm not using anymore that I copied over but ended up not needing, so I deleted the things that used them. I do need to visit a binary expression though, because I've got pluses and arrows, so I had to rewrite what plus and arrow meant. And in my case, plus means the flow on the left and the flow on the right get combined, so I had to implement that somehow. Left arrow also means the same kind of thing. It means the flow on the left and the flow on the right get combined, but they mean something slightly different. So I said, oh, well, where am I going to put that functionality? The right place to put it is inside the flow method, the flow object. So I added a plus and an add upstream to the flow object, which are these two here. And in my case, both of them just go through the array of 10 numbers and just add them together, pointwise add them together. If one of them had a flow of 1 on day 1 and the other one had a flow of 2 on day 1, the end final flow is 3 on day 1. That's exactly how those operators work, right? And the same for every other day. So I only needed plus, and add upstream worked the same as plus, and that's all it does. Those 10-day predictions from 1 day of 1 millimeter of rain today created this way. So I really like that solution. So my plus and my arrow came out nice and easy, and I think everything else was just, everything else just worked out the same, except for when I visit a flow expression. Now, flow expression, remember, is my literal. So when I visit a flow expression, I generate a new flow with the 3 values that were found in that literal. It's ready to roll. Okay, then I jumped over to my locks. And over in locks, I added these lines that would let me see. So first interpret, I created an interpreter visitor, and I call it interpret method by passing in the whole program. It gives me back the final result of the environment. Oops, I need that back. Give me my quick fix. It gives me my final map from string to, like, that's variable name to values, and the only values I'm worried about are flows, so it's from variables to flows. And then I print them all out. So by end of my program, I just print out the final flows for every variable that was computed in the program. So with that done, if I rerun this on the tiny example, on the expression only example, and I didn't compile properly because I don't see a result there. Still don't see a result there. Oh, didn't save. Didn't save. Okay. So when I do the expression only one, which you'll recall doesn't have any variables, there is no special output. It does a whole bunch of stuff internally, calculates some things, but never tells me anything because there was no variables. But if I jump over to my tiny example where there was a single variable that had that same expression, and I execute that one through my evaluator, not only do I get the tokens and the variable, but look, I get a result. The result tells me that there's a variable called only, and its predicted rainfall, its predicted flow from a millimeter of rainfall is 0 liters per second, 4 liters per second, 0. Cool. Nice. So can you see why I've chosen to do my output that way? That's the whole point of this system, is to tell me the flows in rivers. And as I'm going through, I'm realizing that every river is getting one of these variable names. So that's useful. As programs get much bigger, I might want to do something else. I might want to find a way to describe which variables I really need in the output. But for now, I'm just putting every variable on the output. So I run this on the small one, and I get 3 different variables come out, just like I want. And Joe's, so the variance here is being ignored. Just the mean and the magnitude are being used because I'm only doing a simple version. I gotta fix that. So Joe's gets all its rain on day 4, all its flow on day 4, which it gets 4 liters per second. So we can see that Joe gets 0.40000. Mars Creek gets all its flow on day 3, and it gets 4. So we look at Mars Creek, 0.0040000. There's one error here in my program you can probably see. That index 1 should be this day, but because my underlying array is indexed from 0, I'm off by a day. So the 4 mils is coming out there. But then result is Joe's plus Mars. So guess what? It gets the flow from day 1 and the flow from day 3, and no flow on any other days. So just to show you how I would do that, I'll fix that error that I found. That's in flow. Because what's happening is in flow, I'm saying that if the current index is equal to mean, then just spit out all the water, otherwise spit out 0. I need this to be if I minus 1 is equal to mean. So let's recompile, rerun, and nope, it needs to be I plus 1. Yes, I doubled down on my error. All right, so now we're doing. Now Joe's 4 mil is coming out on day 1. Because we're in the real world, not programming world. River managers don't index by 0. So on day 1, the day the rain is falling, 4 millimeters comes out. 4 liters per second comes out of Joe's. No liters per second comes out of Mars. And 4 liters per second comes out of the combined. This is a prediction, remember, because there's just rain falling today, and I'm just predicting how much river flow is there going to be and on this day and future days based on 1 mil of rain falling today. And so my prediction is that the final river system will get 4 liters a second a day, none tomorrow, and another 4 liters a second tomorrow. Finally, let's look at Devlin's, which is the real fun one. And there's lots of other stuff up here because I'm still spitting out the tokens and all that other jazz. But the main action is down in results. And if I just bring up Devlin so you can see the program it comes from. So I'd separated out all the creeks, the upper Joes, lower Joes, Joes, Mars, upper Devlins, lower Devlins, and then the final output of Devlin's Creek. So that's really the one we're interested in, the final output of Devlin's Creek. So if I highlight that one, under my system, when 1 millimeter of rain falls today, I can expect 7 liters a second to come out of that creek today, none tomorrow, 12 the day after, and then none. Okay. So that's my evaluator, that's my parser, that's my expression. I've got a language, it's doing stuff, it's helping me model river systems. Whew, if I wanted to get really fancy, I could graph these results. And as an inspiration to boot off from next, this is what I wanted to provide this for. Okay, yeah, be in touch if you've got any questions about this code. I'm not going to post the full code in a zip file or anything like that, but I've got it on my computer. A lot of it's been on the screen here, but if you're wanting to follow my example through on your own and you're getting stuck somewhere, just post to the forums. That's what they're there for.